So typically when people think about statistical analysis, the first thing that comes to mind are numerical values. However, there's quite a bit that is done with categorical analysis. We're going to talk about contingency tables and notations used for contingency tables, terms of descriptive statistics. We're going to talk about different proportions relative to risks and odds ratios. So what you see here on the right is a contingency table where we have variable X and we have variable Y. Variable X and Y each have one category. These values in the center portion of the contingency table are going to tell us the number of observations that have the value of 1 on variable Y and a value of 1 for variable X. For each of our intersections. So if I have a 1 on X and a 2 on Y, we're going to be in this quadrant and so forth. We also have our total values on the far right side is going to tell me how many observations are going to be the cases when X equals 1 for our observations. And then when we look across the bottom, it's going to give me the totals for each of the categories of my Y values. And the value in the lower right-hand corner of every contingency table is going to equal the number of observations that you have in your data set. Continuing on with our learning objectives, you're going to understand notation used in contingency table analysis, be able to calculate and interpret applicable summary statistics for categorical data, and be able to use multi-layer tables to control for confounding variables. So here would be an example of a contingency table that you would get out of SPSS. This table is displaying two variables. The first one was a response to the question, was the Iraq War worth the cost? Tabulated by the party affiliation across our top. So here your party ID was 1, 2, or 3 for Democrat, Independent, or Republican. And then you had the opinion of 1, it was worth it, or 5, it was not worth it. And so all of this is categorical data. So here you have party ID was marked as 1, 2, or 3 for Democrat, Independent, or Republican, respectively. And then you have your opinion of was it worth it, 5 was not worth it. So once again, this is a little bit easier to describe our categorical data in a tabular form like this. And it shows you, how many Democrats said that it was worth it. So how many of your Democrats said that it was not worth it as well? And you can see their percentages. So here you notice we had 57 Democrats that said it was worth it. And that's going to be equal to 8.2% of my Democrats. And so when I have my 8.2% plus my 91% of my Democrats, I get a total of 100% of my Democrats. So 8.2% said it was worth it, 91.8% said it was not worth it. If we go across and we look at the people that thought that was worth it, we have 57 for Democrat, 151 for Independent, and 294 for Republican, for a total of 502 people that were polled that said that the Iraq War was worth it. And so when we take the sum of these percentages, we get 24.8%. Of the total people that polled that said they felt that that the cost of the Iraq War was worth it was 75.2%. So when we add our 75.2% of those who said it was not worth it, plus the 24.8% who said that it was worth it, we end up with the 100% that we see in the lower right-hand corner. Categorical data is derived from observations of individuals to a nominal category based on that qualitative property, or maybe from observations of quantitative variables that are grouped within specific intervals. Examples could include demographic data, medical treatments and outcomes, political party affiliation, and survey responses. Categorical data is often summarized in contingency tables or a cross tabulation like we saw in our previous slide. So if we look at the contingency table or cross tabulation, it's going to be a tabular representation of the frequency counts for the levels of categorical variables. Level 1.1 is going to be all the observations that have a level 1 for Y and a level 1 for X. N plus 1 is going to be the sum of all the observations that had a 1 for level 1 for variable y. So an example would be political affiliation versus socioeconomic status. If you look at the individual pieces in here, we see that 29 of my independents were from the low socioeconomic status. And I have a total of 996 observations here. So when we look at cell proportion, we're often not as interested as with the absolute counts as opposed to the relationship between our proportions, our cell proportions. So to properly analyze our cell proportions, we need to know the experimental design and relationship between our variables. All of our variables can be considered response variables. So when we know one or more of the response variables with one or more experimental explanatory variable, that can be used in a prospective study or maybe even a retrospective study. Let's say I'm trying to look forward at something, or we're trying to look backwards. It depends on whether or not I'm using a prospective study or a retrospective study. Our proportion notation is when we're talking about our two variables. So pi sub ij is going to give our joint distribution. This joint distribution is describing that individual cell in the middle portion of our contingency table that's telling me the joint proportion of observations that fit for both criteria. Pi I plus and pi plus j are going to be our marginal proportions. And so that's what we see on our sides. The total is going to represent the total for that individual variable. So pi plus 1 is going to be our total for all the observations that responded to level 1 for variable y. And then pi j dash I, or that upward line I, is going to be a conditional distribution of y. So what this means is this is saying, what is my conditional distribution of y given that the level I have for x? So we'll go a little bit more into detail about what that means later, but basically what this is saying is if I look at x level 1 and y level 1, that's going to be what portion of our sample of all of our level x is going to be that level. So that's, what proportion of our value of y is given that we're looking at a particular x level. So I know that sounds kind of confusing, so let's kind of look at an example, and I think it might make a little bit more sense for you from there. So here we have an example of a contingency table showing the breakdown of political affiliation by socioeconomic status, or SES. If you look at this first cell here, you see that the count or number of Democrats that are considered low socioeconomic status is 30. The next value is 34.5%. This tells us that those 30 cases represent 35% of the 87 observations that are low socioeconomic status identify as Democrat. The third value is the percentage of those who identified as Democrats that are low socioeconomic status. So those 30 cases are 9.2% of the 327 observations who identified as Democrat. The last value indicates that those 30 observations represent 3% of the 996 total observations. And this output from SPSS can seem rather cluttered, but it does come in handy in Analytics 1 when you're working with conditional probabilities. It might seem a little awkward now, but it will come more familiar with practice. So let's think about a prospective study. In the case of a prospective study, subjects are either selected or are selected from treatment groups, and then their responses are studied. Sometimes they self-select, so that can be based on people that choose to buy the blue product versus the red product, Or we could just randomly put them into our chart saying I want half of the women in one half and the men in the other half. Or half of the women in the other half. So for an experimental study, our subjects are randomly selected to the treatment groups. If we're going to do an observational study, that means that we're going to look at the groups based on the things that the subjects already have chosen. The principal aim is going to be compared conditional distribution of responses for different levels of explanatory variables or variable. So if we look at enrolled non-disease subjects and we collect baseline exposure data, once again, we know that not everyone that gets exposed gets the disease, then you give them a treatment. And depending on how the study is designed, their treatment can be a placebo or no treatment at all. And then we follow up with them at intervals to get accurate data to compare the incidence of the disease over time. So let's look at aspirin a day versus a heart attack. So here we have findings from an aspirin component of an ongoing physician's health study. So we're looking at people that have been given the placebo and people that have received the aspirin. And then here are the people who have had the heart attack versus those who have not had a heart attack. So people who are taking the placebo and have had a heart attack were a total of 188. People on the placebo who have not had a heart attack is 10,845. People on the aspirin regimen who have not had a heart attack is 104, and people on the aspirin regimen who have not had a heart attack would be 10,933. So here we need to look at are the different number of the different values for the conditional probabilities, so that the numbers make a little bit more sense, and so that we can put them in relationship to each other. So first, let's look at the people who have had the placebo. How many of them, or what proportion of them, have had a heart attack? So we had 188 people who have had a heart attack on the placebo, and our total number of participants, or our total number of people that have had the placebo. So here we have a 1.7% occurrence of people having a heart attack, given that they took the placebo. Here we're looking at the aspirin regimen. So how many people have had a heart attack given they were on the aspirin regimen? So here we have 104 people that had a heart attack, and out of our total of 11,037 people that were on the aspirin regimen, which is 0.94%, now we're going to look at it, given that they've been on the treatment, what's the incidence of a heart attack? So we can make a better comparison, right? So we can see if they're on the placebo, they'll have a 1.7% incidence of heart attack in comparison to the 0.94% incidence of heart attack for those who are on the aspirin regimen. When we do a retrospective study, you're given a response and you look back at the levels of possible explanatory variables. These are often called observational studies. Typically, you're going to oversample from response level of interest. So if you know the overall population proportion, and each response level could be used, you can use Bayes' theorem to estimate the conditional distribution of the direction of interest. So you could look at the patient was on the aspirin regimen, so how many of them had a heart attack? Or, given that they had a heart attack, how many people were on the regimen? So sometimes when you're doing retrospective studies, you can get a bit more insight as to which direction you need to make that conditional probability. And it also allows you to look at specific cohorts of people that you want to evaluate for further investigation. Another example is early forms of oral contraceptives. In a study that took place in England and Wales between 1968 and 1972, looking at heart attacks and oral contraceptive use as my two variables, we're looking at if the person has used the oral contraceptives, yes or no, and if the person has had a heart attack, yes or no. And see, we have our total number of people who have had a heart attack and our total number of people who have not had a heart attack is in our margins, so we call those our marginal values. And so here it would not be appropriate to compare the risk for this study because the column margins are fixed by design and they do not reflect the population marginal proportions. So here we may need to use an odds ratio to estimate our desired relative risk value for this study. So here we're looking at 58 people having had heart attacks versus 166 people having a heart attack. That's not exactly representative of our general population of people who have had heart attacks to begin with. So here we're looking at the descriptive statistics when we're comparing the proportions for binary responses. So that can be differences in proportions, relative risks, and odds ratios. We're going to do an I by J table because there's not really a completely satisfactory way to summarize this association. But when we do it this way, we can use them to get pairs of odds ratios, concentration coefficients, and uncertainty coefficients. Then when we're looking at independence of variables, we can look at our X and Y variables or responses for all of the levels. So if X is explanatory, then the Y response is going to tell me that when my pi ijj given I is going to be equal to my pi of j given I for each of our j, i's, and a's. So basically what this means is my proportion of pi 1, 1, given that it's on level 1, is going to be the same proportion of pi 1, 1, given that it's in pi plus 1. So the proportion would be the same, either way you calculate it. That tells you that your two variables that you're using are independent of one another. So here we have a binary response variable, and we generally are going to compare the responses for different explanatory levels. So when we're looking at this, we have P sub j given I minus P sub j given H. So the difference lies between -1 and +1. Independence is when the difference equals 0 for all I, H, and response level j. So suppose you view party affiliation as an explanatory variable. The difference in proportion for viewing Iraq war was worth the cost. So if we look at it that way, because we have 91.8% for Democrat and 44.3% for Republican, we see that we have a 47.5% difference between our responses and the response rates based on whether or not they were Democrat or Republican. So when we're interpreting the difference of proportions, we need to ask, what is a large difference? This is important in determining whether or not something is significant. A small difference may be more important when pi of j given I and pi of j given H are both near 0 or 1 than when they're around 0.5. So here we have 1 minus 0.001 gives me 0.09. 0.1 is 10 times larger than 0.001. But if you have 0.5 minus 0.41, that's going to give you 0.9. 0.5 is 1.2 times larger than our 0.41. So here, the difference of 0.09 in our first example is 10 times bigger. So it's going to be a much bigger difference compared to still having a difference in 0.09, but only a factor of 1.2 between the two. So here we're looking at our heart attack or no heart attack, and we end up seeing that we have a difference of 0.0076. Relative risk is used when our relative difference between proportions are more relevant than absolute differences. Our relative risk is going to be your pi of j given I divided by your pi j given H. The relative risk of 1 is going to correspond to independence of the two variables. Usually you can't directly calculate this from retrospective studies. So here we see our heart attack and placebo data, and we look at pi of j given I, which is 0.0094 divided by pi j given H, which is 0.017. That gives us a relative risk value of 0.553. Therefore, we can make the conclusion that if we take an aspirin regularly, you can have 0.553 times the risk of having a heart attack compared to those who don't. The way you make this into a meaningful conclusion is you're going to do 1 minus 0.553 and multiply it by 100 to say that this is 44.7% less risky in comparison. Now we have the question of, does age that a woman has her first child at affect the risk of breast cancer? So here we see is first child at age 25 or older in breast cancer or no breast cancer. The risk for having a woman having her first shot at 25 or older is 1.9%. And the way we calculated that was by taking the divided by our total. The risk for a woman having their first child before 25 is 1.43%. So once again, taking your 65 out of your total of 6,168 gives us a relative risk between the two by finding that 1.9% divided by the 1.43% to get a value of 1.33. So what this means is your relative risk is 1.33. So it's higher by 33% if you're over 25. So when you have a 2 by 2 table, row 1 is where you see the odds of being column 1 that have been called 2s, and then row 2 is the odds of being column 1 instead of column 2. So it's the opposite. So you end up with what we call an odds ratio of 0.1 from row 1 divided by row 2. Going back to our breast cancer data, the odds of a woman having her first child after 25 or older and having breast cancer is found by taking the number of women who have had their first child at 25 or older and have had breast cancer, and that number is going to be 31, divided by the number of women who have had a baby over 25 but didn't have breast cancer, which was 1,597. This is going to give you an odds ratio of 0.00194. So the odds for women having breast cancer who had their first child before 25 is going to be 65 for those who did not have breast cancer, and the 4,475 women who had their first child at age 25 or didn't have their first child before 25 and no breast cancer, to give you an odds ratio of 0.0145. So then where do the odds ratio for each of these and do the odds ratio, you end up with a value of 1.34. So what does that mean? That means the odds for women having their first child at 25 or older having breast cancer is 34% more than the odds for women having their first child before 25 with breast cancer. So basically, the conclusion that you can make here is that if you're going to, you're more likely to have an incidence of breast cancer if you had your first child after 25 as opposed to before 25 by about 34% difference if you're going to have breast cancer. So your odds ratios are going to take values that are greater than 0. Sometimes you're going to need to look at the log of your odds ratios. They are univariate to interchanging rows and columns. So it's not really important to specify, which is your response variable. It's not unlike in relative risk that we've looked at before. But you have to specify the variable, and it's equally valid for retrospective and prospective as well as cross-sectional studies. When I look at the odds ratio, I can take my relative risk times 1 minus pi 1 of 2. Divided by 1 minus pi of 1 and 1 given 1. So when the probability of outcome of interest is small, regardless of the row condition, you can use the odds ratio as an estimate of your relative risk. So looking at your heart attack and oral contraceptive use, we're going to use 23, which is the number of yes, you had a heart attack and yes, you used oral contraceptive. Then you're going to multiply it by the number of those who have not had a heart attack and no, they didn't use contraceptive, divided by the opposite proportions from our contingency table to give us about a 2.55 as my relative risk. So when you're going to assess your baseline risk, an example is men who drink 16 ounces of beer a day being 3 times more likely to develop rectal cancer. You need to know the time period of your risk. Sometimes your risks will accumulate with time. An example would be 1 in 9 women will develop breast cancer over their lifetime, but annual risk of women in their 30s is 1 in 3,700, and women in their 70s is 1 in 321. So the other thing you need to think about is investigating confounding factors. An example that would be maybe older cars are almost 6 times as likely to be stolen than newer cars. Sometimes these factors can end up confusing your final results or muddying the water a little bit. So let's talk a little bit about Simpson's paradox. So this is a phenomenon and a way to train appears in different groups of data, but disappears or reverses when the groups are combined. So an example would be the survival rates for standard and new treatment across 2 hospitals. So here we're looking at the data for patients who received the standard treatment or new treatment grouped by if they died or survived. So if we group the data from both hospitals, the risk of dying with the people with the standard treatment was about 595 out of our total that have received the total number of people that have received the treatment of 1,100. So it's about 54% of the people received the standard treatment died. The risk of dying with the new treatment is 905 people out of 1,100 people. So it'd be an 82% risk of dying with the new treatment. So here we see that the new treatment is a little bit riskier than the old treatment, and we end up with a relative risk of about 0.866. If the standard treatment is more risky, or our value would be greater than 1 for our relative risk value. So here we see if we separate the values into 2 different hospitals, we see that Hospital A has a relative risk of 1.06 for our treatment, and then Hospital B has a relative risk of 10. So when our hospitals were combined and the relative risk was a little bit less than 1, but when we separated the 2 groups, both groups gave me a relative risk of over 1. So what's going on? So the point of this is to demonstrate how you present your data can be misleading if we over-summarize our information. So sometimes it's really important to make sure that you have your information separated out into different groups, especially when the subjects are not randomly assigned. So in the case of the hospitals, they weren't randomly selected because patients selected the hospital they wanted to go to for treatment. Let's look at another example. We have college admission bias. So over a given number of years, the University of California, Berkeley admitted 44% of all men who applied to any one of 6 graduate programs and only 30% of women who applied. Clearly, there must be a gender discrimination, right? Well, there's probably some other things that we're not looking at here. So let's look at the admission data for our individual majors. So here we have majors A through F. So let's look at how many applicants of men were admitted versus women that were admitted. One of the things that we can see is that the women are being admitted at higher rates than men for many of these majors. But generally, we see a greater number of women applying to the more selective majors compared to men. So when you're looking at this, you also have to think about the behaviors of the subjects that you're looking at and what's common for the different types of subjects that you're including in your study. Here's one more. We have death penalty sentences results from Florida study, which looks at whether race of the homicide defendant affects the likelihood of the person who had received the death penalty. So if we look at black versus white, we end up seeing that overall we have 290 defendants who did not receive the death penalty versus 36 who did receive the death penalty. The second table shows the percentages across the different groups are both still high for not getting the death penalty. When we add an additional variable such as the victim's race, we now see a slightly different story. So here we see that 100% of the white defendants who had a black victim did not get the death penalty. We also see that 17.46% of the black defendants who had a white victim did get the death penalty. This information can be more valuable in being able to see what kind of biases we have in our data can be very helpful in maybe determining things about the different juries that could be hearing an upcoming case.